Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 18 of Algebraic Topology. In today's lecture, we will discuss starting from Euler characteristic and how to calculate the Euler characteristic, and then we will go on and calculate the homology of a torus. Basically, we will use all the machinery about the simplicial complexes, in particular about the homology of the simplicial complexes and the simplicial pairs, and we will use that machinery to calculate the homology of torus. And then we will have a rough look at how to calculate the homology of a projective plane, and of course we will see what is a projective plane as well. And then we will go on in the last section, we will see how to define homology, because simplicial homology is just one of the many homology theories. So we will see that all of the homology theories satisfy certain axioms, and we will present those axioms, and we will have a look at certain consequences of these axioms as well. So starting from the Euler characteristic of a simplicial complex, if we have a simplicial complex K and a subcomplex L, and if we denote with alpha p of K the number of p simplices in the simplicial complex K, and alpha p K L with the number of p simplices in K which are not in L. So basically we are talking about, so let's say this is simplicial complex K and this is subcomplex L, then basically we are considering this shaded region. So in this shaded region, so alpha p KL is number of p simplices in this shaded region. Okay, now we can define the Euler characteristic of K, the simplicial complex K, as a number of 0 simplices minus number of 1 simplices plus number of 2 simplices up to so on, and minus 1 raised to power n alpha n K. Of course we have minus 1 raised to power n because it depends, so the sign plus minus depends on the number n, if it is even or odd. Similarly, we can define the Euler characteristic of K mod L, which is equal to number of 0 simplices of K which are not in L minus the number of 1 simplices which are K and not in L up to so on, and once again with the minus 1 raised to power n sign, and this plus minus sign depends on whether n is even or odd. Now we have an important consequence of collapsing. So it says that if we have two simplicial complexes or two simplices which are combinatorially homotopy equivalent, then they have the same Euler characteristic. Okay, so let's consider a particular example and see why this is true. So consider this 2 simplex and let's say this is E0, E1, E2, and this shaded region which is 2 simplex is not face of any other simplex in this simplicial complex, so that's why it is free. So and this portion, this edge of this shaded region is free face of this complex. So basically we can collapse this simplex, this shaded simplex, because it has this free edge. Okay, so after collapsing this we get the following shape. So let me say again, we have this 2 simplex which has a free edge, free 2 minus 1 face, okay, because we need a free p minus 1 face as well. So in this case we have a free 2 minus 1 which is 1 face, so we can collapse it to this. So basically after collapsing, let's call it K and let's call it K prime. So after collapsing K along this 2 simplex with this free edge, we get this portion. Okay, now let's calculate the Euler characteristic of K and Euler characteristic of K prime, and let's see what's the difference between them. So the Euler characteristic of K is equal to number of 0 simplices, so the number of 0 simplices is 3, minus the number of 1 simplices which is the number of edges, so 1, 2, 3, so there are 3 edges, plus the number of 2 simplices which is only 1 in this case, so this is equal to 1. Now let's calculate the Euler characteristic of K prime. So number of zero simplices. So there are 3 number of zero simplices minus what is the number of one simplices, so 1 2. Okay, so and there is no 2 simplex, so which is equal to 1. So as we have seen that after collapsing a simplex, a 2 simplex in this case, there is no change in the Euler characteristic. Okay, so in general we can prove this result, but the proof, in general proof, is not included in this course. Now let us now connect Euler characteristic and simplicial homology of oriented simplicial complex and the simplicial pair. So to proceed further, we need the definition, the following definition of Betti numbers. So how we define the pth Betti number of a simplicial complex K? So basically this is the rank of the homology group HPK, and we know how to calculate the rank of an abelian group. And similarly the Betti number of K mod L is basically equal to rank of this HPKL, so this homology of the simplicial pair. Now we have the following theorem which connects the Euler characteristic and the homology groups. So basically these are the pth Betti numbers, which is rank of HP of K. So that's how we connect this Euler characteristic with the homologies, and similarly this Euler characteristic of K mod L with the homology, this relative homology of simplicial pair. Let's see how to prove this first part, and the second part is very similar to this. Okay, so to prove this part, consider the following sequence of abelian groups. So when we want to calculate the homology of this simplicial complex, then we consider this sequence. Okay, so where C and K is basically the free abelian group generated by the n simplices of K, and these are the boundary maps, and once again the free abelian group generated by n minus 1 simplices of K, and there is 0 over here because we impose that this K has dimension n. Okay, now we want to show the following thing. Okay, so what is this expression? Of course this is basically Euler characteristic of K. So in other words, we want to show this equality, or in other words we want to show that for P is equal to 0 to n minus 1 raised to power n alpha P K minus beta P K. Okay, so this is equal to 0. Okay, so these two are equivalent, so basically we will be showing this thing. So let's see how to proceed further. Now we know that from this sequence CPK to CP plus 1 K up to so on, and coming from this, so this is partial P plus 1, so partial P. Okay, so coming from CP plus 1 of K. Okay, so we have this chain complex. So from this chain complex we see that what is kernel of partial P? So kernel of partial P is basically set of elements of CPK such that partial P of X is equal to 0. Okay, so that's how we define. Now we can easily see that this is contained in CPK because this is a set of elements of CPK. So we can say that there is an inclusion map from kernel of partial P to CPK. Okay, now similarly we have this image of partial P. So what is image of partial P? So basically so it should be P minus 1. Okay, so image of partial P is basically a set of elements of C P minus 1 of K such that there exists Y belongs to CPK and partial P of Y is equal to X. So basically this is set of all elements of CP minus 1K which are images of elements of CPK. Okay, so we can see that this map is surjective. Okay, because every element of this image of partial P is image of some element of CPK, so this is surjective. Okay, now what this short exact sequence is saying is that CPK quotient with kernel of partial P is isomorphic to image of partial P. And if you remember, then this is the first theorem of isomorphism of modules. Okay, so because these are Z modules. Okay, so this statement can be written in this way as well. Okay, so because this is a short exact sequence, because the image of I, which is kernel of partial P, okay, so the image of I is equal to kernel of this surjective map. So this surjective map is basically partial P. So kernel of partial P, because this is inclusion map, so kernel of partial P lives inside Cp of k, so we can say that the elements of Cpk which will be mapped to basically 0 are these elements. Okay, so the kernel of this partial P is equal to is basically written over here. Okay, so we have this short exact sequence, and this is equivalent to this first theorem of isomorphism. Okay, now similarly we know that HP is basically equal to, so at this point if we want to define the homology, so this is equal to a kernel of partial P quotient with image of partial P plus 1. Okay, now we can write down this fact in this short exact sequence as well. So once again, how we can write it down, because this HP is quotient of these two, and so this is obvious from here, because we have seen from the definition and from the discussion of short exact sequences that this element is basically the quotient of this element with this element. Okay, now if we have this short exact sequence, then from this short exact sequence we can write down that the rank of CPK is equal to the rank of this plus rank of this. Okay, but the rank of CPK means the number of P simplices in K. Okay, so that's why this is equal to alpha P. Okay, so remember that we denote by alpha pk by the number of P simplices in K. So that's why we can write down alpha P is equal to rank of this plus rank of image of partial of P. Okay, so this is basically coming from the discussion of our exact sequences or short exact sequences, that given this kernel of partial P and this question mark and image of partial P goes to 0, then this element is basically can be taken as the direct sum of these two elements. Okay, so that's why this the rank of this is basically equal to the rank of this plus rank of this. Okay, so if you remember, as a particular example, we considered that if this is the question mark, then and if we have this short exact sequence, then this question mark can be taken as Z plus Z, so the direct sum of this and this. Okay, so that's why the rank of CPK is equal to rank of this plus rank of this, and using the same fact, the rank of this is equal to rank of image of partial P plus 1 and rank of HP. Okay, now what is rank of HP? From the definition of Betti number, this is beta P. Okay, so that's why we can write down beta P is equal to rank of kernel of partial of P minus rank of image of partial of P. Now from our above discussion, we can see that alpha P minus beta of P is equal to rank of image of partial of P plus rank of image of partial P plus 1. Okay, now if you use this expression and try to write down this sum, then on this side which will be 0 eventually, is basically equal to alpha naught minus beta naught, okay, minus alpha 1 minus beta 1 up to so on, plus minus 1 raised to power n alpha n minus beta n. Now this alpha naught minus beta naught is basically equal to rank of image of partial naught plus rank of image of partial p plus 1. Okay, so when you replace these values for each and every term like this, then at the end they will cancel out each other, and at the end you will get 0. So that's why we have 0 over here. So that's what we wanted to prove, because if this holds, then this implies that p is equal to 0 to n minus 1 raised to power p alpha p, which is basically the Euler characteristic of k, is equal to the alternating sum minus 1 raised to power p is equal to 0 to n and beta p. So the alternating sum of the ranks of the homology groups. So that's how we link Euler characteristic with the homologies. And similarly, if we consider the following chain and following each and every step that we did in the previous part, we can show the second part of the theorem, which says that this Euler characteristic of KL is equal to the alternating sum of the Betti numbers of this relative homologies. Now let's have a review or recall of our previous discussion. So it says that if we have a simplicial complex, then its underlying space is denoted by mod k, and basically it's just the space in the ambient Euclidean space. Okay, so for example, if we have this simplicial complex, it has these red nodes and these green 1 simplices and these blue 2 simplices, and then mod of k, or the underlying space of the simplicial complex, is just this space, because it lives in some Euclidean space. For example, it lives in R3. So we are talking about that space of R3 which was occupied by this simplicial complex k. Okay, so in other words, we are forgetting about the vertices, the edges, and the 2 simplices. So we are forgetting everything about the simplicial structure about this simplicial complex, and we are just taking it as a set of points in R3. Now the following observations are obvious. So once again, if we have a simplicial complex and a subcomplex L, then the following is obvious, because this chi L calculates the alternating sum of 0, 1 and 2 simplices up to n simplices of this subcomplex L, and chi KL calculates the alternating sums of 0, 1, 2 up to n simplices of this region which is k minus L. Okay, so this is k minus L region. So this curly shaded region, and this straight line shaded region is L. So of course, when we are calculating these alternating sums, then the Euler characteristic of k is equal to the sum of these numbers. Okay, so if k is a simplicial complex and L1 and L2 be 2 subcomplexes of k, then the Euler characteristic of their union is equal to Euler characteristic of L plus Euler characteristic of L2 minus the Euler characteristic of their intersection. So once again, if we have this subcomplex L1 and subcomplex L2, and if we are counting the number of 0 simplex and 1 simplex up to n simplices in this region twice, then we have to subtract them as well. Okay, now we have the following theorem which will help us in calculating the simplicial homology of a torus. So if we have a 2-dimensional simplicial complex, and if the underlying space is enclosed by a simple closed polygon, then the Euler characteristic is 1. And similarly, if we have a 2-dimensional simplicial complex, and if the region defined by this simplicial complex, or the underlying space, is enclosed by a simple closed polygon, and M is obtained by deleting a 2 simplex from K, then M and boundary of K are combinatorially homotopy equivalent. Okay, so for example, if you have this region, okay, so let's take it as a simplicial complex. Okay, so this goes here, this goes here, so these are the vertices, and let's say there's another one, so these are the vertices. Okay, so consider this simplicial complex, and of course these shaded regions are included. It's a 2 simplex, and just assume that we delete this region, so this blue shaded region. So if we delete this 2 simplex from this simplicial complex, then this is this region M. Okay, so and M is obtained by deleting a 2 simplex from K, then M and boundary of K. Okay, so the boundary of K is this thing. Okay, so 1 2 3 1 2 1 2. Okay, so this is the boundary of K. So these two, so the M with the 1 2 simplex deleted from K, and this partial K, which is the boundary of K, are combinatorially homotopy equivalent. And why this will be related? Because we know that when two simplicial complexes are combinatorially homotopy equivalent, then they have the same homologies. Okay, so we are going to use this fact when calculating this simplicial homology of a torus. So we know what is a torus. It's basically a tube-like or donut-like object shown in this picture. Now we want to triangulate this torus. Now from the quotient topology, we know that this torus and this square are the same when we take the quotient of this square by identifying these two sides and identifying these two sides. Okay, so how to identify? So basically we identify this points, so we and these points. Okay, so at the end these 4 points of the corner, they become only 1 point, so that's why it is exactly 1 point, because when we are calling this square as a torus, then it means that I'm taking this vertex and this vertex as the one vertex. Okay, they are written separately, but of course after taking quotient they become the same vertex. Okay, and since we are taking this square as a torus, so we are taking this torus after so we are taking the square after taking the quotient. Okay, so that's why although there are 4 different corners, but for us it is the same corner, because after taking quotient it becomes the same corner as a torus. Okay, now the next problem is to triangulate this torus. Okay, so how to triangulate this torus? We basically divide it into the following portions. Okay, and we name this as 2 3. But now, since once again using the same argument, this is a torus, which means that it is not really a square. We are imagining this square as after taking the quotient. So when we identify this side with this side, then they are the same side. So in other words, if we have named this as 2 and 3, then this must be 2 and 3 as well. Okay. Similarly, if I name this as 4 and 5, and since we are going to identify these two sides, so this is 4 and 5. Okay, and then we can name it as 6, 7, 8 and 9. And how to triangulate this thing? So we triangulate them by considering these two simplices. Okay, now as you can see that we have two simplices and all of this region is basically covered by these two simplices. So what two simplices? So the two simplex 1 to 6. Okay, so there is orientation in these regions as well. Okay, so I'm taking the orientation to be clockwise. Okay, now observe that we are taking the orientations of these two simplices which is compatible with the orientations of the other two simplices in this simplicial complex. So for torus, fortunately we can do that, and that's why torus is called orientable surface, and unfortunately we can't do it in general, and those kind of surfaces are called non-orientable, and you can easily find it in the reference books if you want to read these things further. Okay, so we have a triangulation of the torus. Okay, now we want to calculate the simplicial homology of this torus using this simplicial complex. Now what we do is, so let's call this triangulation T, and we delete this two simplex which is colored red in this picture, and after deleting this two simplex we call the new simplex or simplicial complex as T naught. Okay, now we are going to use T naught and T, and of course you can judge that we are going to use the relative homology of this simplicial pair to calculate the homology of this torus. Now let us calculate the simplicial homology of the pair. So if we want to calculate the simplicial homology, we should know that we have this sequence C2 TT naught goes to C1 TT naught goes to C naught TT naught. Okay, so this simplicial complex T is basically two-dimensional, so there will be no C3 and higher abelian groups. Now let's have a look at C naught of TT naught, what it should look like. So basically it is equal to C naught of T quotient with C naught of T naught. So in other words, what we are saying is the free abelian group generated by the zero simplices of T and the free abelian group generated by zero simplices of T naught. And now we can see that we obtained T naught from T by deleting 1 2 simplex, and we haven't deleted any zero simplex or any other one-dimensional simplex, so we just deleted this 2 simplex, this triangle, this red triangle 6 7 9. So in other words, the number of zero simplices in T and number of zero simplices in T naught are the same, so that's why this must be equal to 0, because these are the same groups. So after taking the quotient, it should be a 0. Okay, so of course you remember that this 0 means the 0 module. So what about C1? Once again we haven't deleted any one simplex from T to obtain this T naught, so if we have a look at this, then this is equal to C1 of T quotient with C1 of T naught. So in other words, we can say that this is exactly equal to 0. Now let's come to C2 of TT naught. What will be the difference between the two simplices of T and T naught? Of course we just deleted only 1 2 simplex from T to obtain T naught, so we can say that the difference or this quotient, okay, so in this quotient this group C2 of T has 1 extra element. Okay, and this free abelian group generated by 2 simplices has 1 extra element, and this C2 of T naught has 1 less element. So in other words, if for example if the rank of this is x, then the rank of this is x minus 1. Okay, if the rank of C2 of T is x and rank of C2 of T naught is x minus 1, then their quotient must be of rank 1. It means this is isomorphic to Z. Okay, so we have the following sequence now. Okay, so this Z is C2 of TT naught, this 0 is C1 of TT naught, and this 0 is C0 of TT naught. Now let's calculate the relative homology. So H2 of TT naught, so this is equal to the kernel of partial 2 quotient with the image of partial 3. So as you can see that there is 0 over here, so the image of partial 3 will be 0 because partial 3 is a homomorphism, is a Z module homomorphism, so the image of 0 must be 0 inside Z. So this is just 0 module. And what about the kernel of partial 2? So once again you can see that there is 0 over here, so everything from C2 of T naught is going to 0, so the kernel of partial 2 is equal to C2 of TT naught. Okay, and image of partial 3 is 0, so this will be exactly isomorphic to C2 of TT naught, but this is isomorphic to Z, so we can say that H2 of TT naught is equal to Z. Now let's calculate what will be H1 of TT naught. So we are here at this node, which is C1 of TT naught, so which is equal to the kernel of partial 1 quotient with the image of partial 2. So the image of partial 2 is 0 and the kernel of partial 1 is 0, so this is equal to 0. So once again let's calculate H0 of TT naught. So this is equal to, so the kernel of partial naught, which is 0, and the image of partial 1, which is 0, so this is equal to 0. Okay, so we have calculated the relative homologies of this simplicial pair. Now we have triangulation of the torus as T, and after removing 1 2 simplex we obtain this T naught. Now we can continue collapsing 2 simplices of this T naught and we obtain square. Okay, so why this is true? Because we have proved in this theorem that if we have a 2-dimensional simplicial complex and if the underlying space is enclosed by a simple closed polygon and M is obtained by deleting 2 simplices from K, then M and the boundary of K are combinatorially homotopy equivalent. Okay, so using this result we can say that this T naught, okay, so for a moment forget about the fact that this one, so all the 4 vertices are same, and this 2 and this 2 3 are same, so let's forget about this fact and just look at this square as just a square and triangulate it. Okay, so this is basically a 2-dimensional simplex, and we deleted this red portion, this 2 simplex from here, so it becomes another simplex, and this simplex is combinatorially homotopy equivalent to the boundary of this simplex, so it becomes the following. Okay, so this is the boundary of this 2 simplex. Okay, now this T naught prime, okay, so what is T naught prime? So just ignore the fact that 1 2 3 and these elements are the same. Okay, so just consider this fact that we are considering this square, and these are the triangulations, and these are the 2 simplices. Okay, so just consider this thing and remove this 2 simplex from here, and after removing this 2 simplex from here we get another 2 simplex, and by that theorem which we saw earlier, this will be combinatorially or combinatorially homotopy equivalent to this boundary of K. Okay, so these 2 are equivalent, but now let's rewrite these numbers, because this vertex is now 1, this is 1, this is 1, this is 1, this is 2, this is 3, and once again this is 2 3, and this is 4 5, and this is 4 5. Okay, so what does this become? So once again, these four vertices which are ends of this square are not different vertices, they are the same vertices. Okay, so we can sketch another simplex which will be representing the fact that these four vertices are the same. So we can do it in this way. So consider this simplex now. So in this simplex you can see that there is an arrow from 1 to 4. So there is an arrow from 1 to 4. 4 goes to 5, so 4 goes to 5, 5 goes to 1, 5 goes to 1, and then consider this. So 1 goes to 2, so this is the arrow, 2 goes to 3, this is the arrow, and 3 goes to 1, this is the arrow. Okay, so these four vertices, which is exactly one vertex, and so this becomes, so this picture becomes this. Okay, so in other words, we can see that this T naught is combinatorially homotopy equivalent to this one simplex. Okay, because this square, which is the boundary of T naught, and with these names of vertices, so this square and this one simplex are the same. So T naught is homotopy combinatorial equivalent to this. And why this is important? Because we know that if we have two simplicial complexes K and L which are combinatorially homotopy equivalent, then they have the same homology groups. Now we are going to use this fact. So in other words, we are going to calculate the simplicial homology of this simple object, and the simplicial homology of the simple object, they are going to be isomorphic to the simplicial homology of T naught. So let's calculate the simplicial homology of this object. Okay, so to calculate the simplicial homology of T naught, we calculate the simplicial homology of this object. Let's call it T naught prime. So how to calculate the simplicial homology? So you can see that it is a one-dimensional simplex. So if we consider this chain complex of T naught prime, then C2 will be 0, C1 of T naught prime, and then C naught of T naught prime equal to 0. So this C2 is 0, and there will be 0 on the other side. Okay, so in other words, we can say that H2 of this T naught prime is 0, because this is equal to the kernel of partial 2. So the kernel of partial 2 is basically 0, because C2 is 0, and quotient with the image of this partial 3. So once again this is 0. So H2 of T naught is 0. Now let's calculate H1. So in other words, I want to calculate the kernel of partial 1. So in order to calculate the kernel of partial 1, I need to calculate what kind of elements of C1 of T naught prime goes to 0. So what is the general element of C1 T naught prime? So a general element of C1 T prime is basically an integer combination of the one simplices of T naught prime. So what is an integer combination of one simplices of T naught prime? So what are the one simplices? 1, 2. So 1, 2 plus A2 into 2, 3 plus A3 into 3, 1 plus A4 into 1, 4 plus A5 into 4, 5 plus A6 into 5, 1. So now we assume that partial 1 of this is equal to 0. Now let's calculate partial 1 of this. So partial 1 is homomorphism, so it will not affect this integer a1. So what is the boundary of 1, 2? So the boundary of 1, 2 is going to be equal to 2 minus 1. Okay, so a1 into 2 minus 1 plus a2 into 3 minus 2 plus a3 into 1 minus 3 plus a4 into 4 minus 1 plus a5 into 5 minus 4 plus a6 into 1 minus 5 equal to 0. Okay, so collecting the coefficients of the same element, so minus a1 plus a3 minus a4 plus a6, so these are the coefficients of 1. Similarly, collecting the coefficients of 2, so a1 minus a2 is equal to 0, so these are the coefficients of 2. So coefficients of 3, a2 minus a3 is equal to 0, and coefficient of 4, so we have a4 minus a5 equal to 0, so this is the coefficient of 4, and then the coefficient of 5, so this is basically a5 minus a6 equal to 0. So these are the condition under which this element will go to 0, which is the general element of C1 of T0 prime. Now these conditions imply that, so if we consider these conditions, so they imply that a1 is equal to a2 is equal to a3, and a4 is equal to a5 is equal to a6. If we use these conditions, then the first equation is satisfied. So we have the following solution. So in other words, we can say that the kernel of C1 of T0 prime is basically equal to alpha tau 1 tau 1 plus alpha 2 tau 2. So what is tau 1? So tau 1 is basically equal to a1, a2, a3, so the coefficients of a1, a2, a3, so basically 1, 2 plus 2, 3 plus 3, 1, and what is tau 2? So a4, a5, a6, so a4, a5, a6, so since they are equal, so we can take a4, a5, a6 common, and we will get the element 1, 4 plus 4, 5 plus 5, 1. Okay, so this is the kernel, and you can see that this is generated by two elements, or the rank of the kernel is 2. Okay, so this implies that the kernel of partial 1 is isomorphic to rank 2 Z module, which is isomorphic to Z plus Z. Now we have the kernel, and what about the image? So the image of partial 2 of course is 0, so we can say that H1 of T0 prime is isomorphic to Z plus Z. So let's now calculate H0 of T0 prime. Okay, so to calculate the H0 of T0 prime, we see that what is the rank of C0 of T1 prime. So basically this is isomorphic to, so what is the number of zero simplices? So 1, 2, 3, 4, 5, so this is isomorphic to Z plus Z plus Z, so 5 copies of Z, so 1, 2, 3, 4, 5, so it is isomorphic to this. Okay, now let's have a look at this C1 of T0 prime. It is basically 1, 2, 3, 4, 5, 6. So the rank of C1 of T0 prime is 6, and the kernel of partial 1 is basically equal to rank 2 inside C0 T1 prime. So if we consider this short exact sequence, which we have already used in today's lecture, so it says that kernel of partial 1 goes to C1 T0 prime, goes to image of partial 1 goes to 0. Okay, and we already we also know that the rank of this is equal to rank of kernel of partial 1 plus image of partial 1. Okay, so the rank of this we already know, it is basically 1, 2, 3, 4, 5, 6. It is 6. Okay, so isomorphic to Z6. And what about kernel of partial 1? We proved that this is isomorphic to Z2, so 2 copies of Z. So using this thing, so 6 must be equal to this 2 and this unknown, so this must be isomorphic to Z4. So the rank of image of partial 1 is 4. So in other words, the image of partial 1 inside C0 T1 T0 prime, it has rank 4. And what about the rank of the kernel of partial naught? Okay, so H0 of T0 prime, which is equal to kernel of partial naught quotient with the image of partial 1. So the kernel of partial naught is basically 5, has rank 5, because C0 T0 prime has rank 5 and everything is going to 0 by this partial naught. So that's why this is isomorphic to, so this 5 minus the 4, which is the rank of the image of partial 1, so this is isomorphic to Z. So we have calculated the homology of T0 prime, which is combinatorially homotopy equivalent to T0. Now we have the following situation, that we have a subcomplex T0 of T, and we know the homology of T0, and we also know the relative homology of TT0. So and we also have this short exact sequence of simplicial complexes, and from this short exact sequence of simplicial complexes, we have the following sequence of homology groups. So 0 to H2. So we are talking about 2-dimensional simplices, so H3 and higher groups will be 0. So H2 of T0 goes to H2 of T goes to H2 of TT0 goes to H1 of T0 goes to H1 of T goes to H1 of TT0. So this goes to H0 of T0, and this goes to H0 of T, and this goes to H0 of TT0, and this goes to 0. Now we have calculated the following information. So H2 of TT0 is isomorphic to Z. Okay, H0 of T0 is 0, H1 of TT0 is 0. Okay, and we also know that H0 of TT0 is isomorphic to Z. Okay, and we also calculated H2 of TT0, and this is equal to 0. Okay, so we calculated these relative homologies, and we calculated the homologies of T0 as well. So we know what is H2 of T0, we know what is H1 of T0. So H1 of T0 is isomorphic to Z plus Z, and we also know what is H0 of T0. So we have 1, 2, 3, 4, 5, 6 information in this, and what is left is these information. Now one thing is very clear, we have 0 on these two sides, so in other words this must be isomorphic to this. So for torus, H0 of T is isomorphic to Z. Okay, because these must be isomorphic. So once again, this is coming from our discussion. We did a corollary and using the exactness of this sequence. The corollary says that if these two are 0, then they must be isomorphic. So we have H0 for the torus. So in order to calculate H1 and H2, we need to understand this map from H2 of TT0 to H1 of T0. So let's try to understand this map. So to understand the map between H2 of TT0 to H1 of T0, so consider the following diagram. So 0 goes to C2 of T naught goes to C1 of T naught goes to C naught of T naught goes to 0, and this is coming from C2 of T, this is coming from C2 of T naught and coming from 0. So C1 of T naught goes to C1 of T goes to here, and we have these maps as well, and from here we have C naught of T goes to C naught of T naught up to 0, and these goes on, and these are the boundary maps: partial 3, partial 3, partial 3. These are partial 2, partial 2, partial 2, and these are the boundary maps: partial 1, partial 1, partial 1, and partial naught, partial naught, partial naught. Okay, so we have already seen this commutative diagram. Now we want to see the image of elements of H2 of T naught. Okay, now in other words, you can see that H2 of T naught is equal to the kernel of partial 2 quotient with the image of partial 3. Of course, the image of partial 3 is 0, so this is exactly equal to the kernel of partial 2. Okay, so this is just Z2 of T naught. Okay, also what is C2 of T naught? So C2 of T naught is equal to C2 of T quotient with C2 of T naught. Okay, now we also remember from our discussion of this connecting homomorphism. Okay, so this is basically connecting homomorphism. So how to define this connecting homomorphism? So the image of some element of C2 of T naught, let's say as Z. Okay, so this is equal to some element omega of C1 of T naught, such that there exists an element sigma over here, and such that there exists sigma belongs to C2 of T, and partial 2 of sigma is equal to, so this inclusion. Okay, so let's call this I, so I of omega. Okay, now let's have a look how many elements, or what is the rank of C2 of T naught. So the rank of C T naught is 1, because there is only one element different from C2T and C2T naught. We have already seen it. So let's call the generator of this rank 1 abelian group to be sigma tilde, and corresponding to this sigma tilde there will be an element in sigma in C2 of T, because this is surjective. So this is surjective map, so this sigma tilde will be image of some element, and we are calling it sigma. And what is this sigma, by the way? We know what is sigma because this is the triangle. So let's go back and see what is this sigma. Okay, so it is this triangle 6, 7, 9. Okay, so we are taking this clockwise direction, so it is 6, 7, 9. So the triangle 6, 7, 9, or the 2 simplex. Okay, now what is the boundary of this 2 simplex? Because this boundary partial 2 of sigma will be equal to omega, because this I is inclusion map. Okay, so this omega is basically equal to the boundary of this sigma. So what is the boundary of this element? So we can calculate the boundary. So basically we have W to be equal to 7, 9 minus 6, 9 plus 6, 7. So that's the image of this sigma tilde from H2 of T naught to H1 of T naught. Okay, but this omega is an element of C1 of T naught, and we want to see what will be its class in H1 of T naught. So what will be the class of omega in H1 of T naught? Now observe that we can now there exists an element, let's call it D, which belongs to C2 of T naught. Okay, and the boundary of that element is equal to omega. So what is that element? So this element D is equal to 1 to 6 plus 164 plus 276 plus 237 plus 347 plus 314 plus 468 plus 485 plus 679. Okay, so not this element because we have deleted this, plus 698 plus 745 plus 759 plus 521 plus 582 plus 893 plus 832 plus 951 plus 913. Okay, so the boundary of this element D is equal to minus omega. Okay, so in other words, this omega, which is an element of C1 of T, and this is the image of this sigma tilde, and the class of this omega is 0, because in H1 of T naught we have omega, the class of omega, but if this minus omega belongs to the boundary, in other words, this H1 of T naught, which is equal to the kernel of this partial 1 quotient the image of this partial 2, and the kernel of this partial 1. Okay, so we are taking the element of this to be omega, and if the same element belongs to image of partial 2, then of course this omega is 0. So we can say that this implies that this map, which is coming from H2 of T naught to H1 of T naught, is a 0 homomorphism. Okay, so it's a 0 homomorphism. So what is the impact of this result? Let's go back to our sequence. Now this star is basically a 0 homomorphism. Okay, so if this is a 0 homomorphism, so in other words everything is going to 0 on this side, so we have the following situation: H2 of T goes to H2 of T naught goes to 0. So in other words, these two are isomorphic, so we have calculated another homology group of the torus, and this is H2 of T, which is isomorphic to Z. Now if this is a 0 homomorphism, so the image of this, so this sequence of groups is exact, so the image of this must be equal to kernel of this. Okay, so if the kernel, okay, so the image is 0 and the kernel is 0, and we have also 0 over here, so we can say that these two are isomorphic, so we can say that H1 of T is isomorphic to Z plus Z. Okay, so that's how we calculate the homology of a torus. Now let's calculate the homology of a projective plane. So what is projective plane? So we are not going to define it very precisely. So projective plane over the real projective plane is basically collection of all lines in R3. So in R3, set of all lines passing through the origin. Okay, so in other words we can say that set of all one-dimensional vector spaces of R3. Okay, so set of all one-dimensional vector spaces of R3 is basically set of all lines passing through origin in R3, and if we want to write down all of these lines in a set, then we want to represent each and every line with one point. And an easy way of doing that is take a hemisphere, and corresponding to every point on this hemisphere there is a line, and corresponding to every line there is a point on this hemisphere. So we can say that this hemisphere is basically projective plane. Now we can flat, or we can project this hemisphere onto a disk in R2. So we can say that a projective plane is basically, a real projective plane is basically a disk in R2. Now we want to triangulate this disk, and when we are triangulating this disk, it means that we are triangulating the projective plane. So one triangulation of this projective plane is take this triangle and consider triangles like this. Okay, so this is basically 1 1 3 3 and 2 2 and then 4 5 6. Now you can see that it is not really a simplicial complex, because we have some curved boundaries, but if we flat these boundaries with straight lines, then these two are basically homeomorphic to each other. So we can consider these curved lines as straight lines going from 3 to 2 and 2 to 1 and 1 to 3, 3 to 2, 2 to 1 and 1 to 3. Okay, so basically this is a simplicial complex now, and we can calculate the homology of this simplicial complex. We can use the same tricks. Basically let's call it T, and we can delete this 2 simplex and we can call it T naught, and using the same tricks that we use to calculate the homology of a torus, we can calculate the homology of a projective plane. Now let's come to our last topic of discussion of today's lecture. So axiomatic definition of homology. So far we have studied simplicial homology, but there are other kinds of homologies as well. So for example, singular homology, de Rham homology, Check homology, cellular homology, up to so on. Now Eilenberg and Steinrod formally gave the axiomatic definition of a homology theory. So basically there are many homology theories. Then what is homology then? So they gave this axiomatic definition, and any homology theory satisfying these axioms is a homology theory. Okay, so what are the axioms? So before going to the axioms, let's recall the definition of a topological pair. So pair of topological spaces consisting of a space X and a subspace A is called a topological pair, or just a pair. And 2 maps of pairs are homotopic if there is a map of pairs F from X cross I, A cross I to YB, okay, such that fx0 is f of x and fx1 is equal to g of x for all x belongs to T. Okay, so these are basically very similar to our discussions when we were doing homotopies. So what are the axioms? So the axioms are presented over here. We have a class of topological pairs, and such that the following happens. If we have xa belonging to this class of topological pairs, then xx, x phi, a phi, aa, x cross I, a cross I belongs to A as well. And similarly star phi, where star denotes the space of one point, also belongs to A. Now a homology theory on A, the class of topological pairs, consists of the following objects. Okay, and these are the objects, and these objects satisfy certain conditions. We will go to those conditions later on, but let's see what are the objects of this homology theory. So corresponding to each pair there exist abelian groups HQ XA. Okay, similarly for each map of pairs there exists a homomorphism from HN XA to HN YB. And we have also this homomorphism HN XA to HN minus 1 A phi. Okay, so let's see what are the conditions satisfied by this. So these are the axioms. If we have this F to be identity map, then this F lower star is also identity map between the homology groups. If F and G are given, then F circle F, so this composition star is equal to G star circle F star. Similarly, if we have F, which is a map of pairs, then the following diagram commutes. So there is a diagram which is basically Hn xa goes to Hn yb. So this goes to Hn minus 1 a phi, Hn minus 1 b phi. So this diagram commutes. So fourth axiom is basically the following sequence is exact, and you can see that you can basically identify them because these are the same properties that we studied for simplicial homologies, and when we are writing down over here, then we are talking about relative simplicial homology or simplicial homology of a pair, and we also proved that this is exact sequence if we take X to be simplicial complex and A to be a subcomplex. Okay, and we have homotopy axiom. If F and G are homotopy of pairs, then F star and G star are equal. And we have excision axiom, which says that if we have a pair and U is open in X, and the closure of U is contained in the interior of A, then the inclusion map induces an isomorphism. And in the last we have dimension and this eighth. So dimension means, so homology of a point is Z if n is 0, and this is 0 if n is not equal to 0. And the last axiom is, for each alpha belongs to Hn, there exists a pair of compact spaces in A such that alpha is equal to image of J star, where J is equal to this, an inclusion map. So I'm not giving explanations to this because this material will not be examined in your examinations. Okay, so these axioms and this axiomatic definition of homology is only included just for the sake of perfection, and just to tell you that there is something like this which exists. Now just using the axioms we can easily derive these things. So what is S naught? S naught is basically minus 1 and 1 points. Okay, so we can see that H naught of S naught is Z plus Z because it has two connected components. So for each connected component we have a copy of Z, and all of these groups, higher groups, will be 0 because there is no one simplex and higher simplices. If we name delta minus 1 and delta plus 1 as plus 1 and minus 1, then by excision we can derive that they are isomorphic. And from the dimension axiom, because this delta plus is just a point, so from dimension axiom this must be isomorphic to Z. So we can see that we have calculated this relative homology of these two topological spaces just by looking at the axioms. So this is one of the useful things about these axioms as well.